Hi. So we're going to be working in section 8.2 here. We're working on confidence intervals, and in this video, we're going to learn how to calculate a confidence interval when sigma is unknown. Okay. That's a section 8.2. So the first thing I wanted to do, I always like to bring us back to the formula card, because the formula card is, it's what you get to have with you when you take your tests. So this is the formula card. And I'm just scrolling down to chapter 8. And I see here in chapter 8, here is the formula that we're going to discuss now. It's this is the Z interval for mu when sigma is known, right? And for large sample sizes, okay? We're just really going to use this when sigma is known here. And so I'm going to go over to the board. Let's go over to the board. You saw how it was written with the plus and minus. I always write it a little different in that I write it as the plus and minus. This is what it means: x bar minus z sub alpha over 2 times sigma over the square root of n to x bar plus z sub alpha over 2 times sigma over the square root of n. Okay, so it turns out, like, what we had been doing, and let's see, this is what we had been doing with our confidence, the intervals that we worked with, say the 9.544% interval, was we were looking at x bar minus 2 times sigma over the square root of n to x bar plus 2 times sigma over the square root of n. And we said that that was the 0.9544% interval. So what we're going to want to have is a way of getting a desired confidence level. So for any confidence level, right? If you give me a confidence level, maybe we'll call that CL, right? Then I should be able to calculate a confidence interval. And in order to get that confidence level to be just what I need to be able to adjust the coefficient of sigma over the square root of n, right? So it worked for the 3 values we were playing with for the empirical rule values. But in general, what I report to my clients is not a 9.544% interval, but a 95% interval or a 99% interval, sometimes a 90% interval. But so we want to be able to have the ability to give me a confidence level, and I can tighten that estimate up a little bit, the confidence interval, or I can loosen it up. So what we want to do now is go over this relationship between z sub alpha over 2 and the desired confidence levels, right? So we have 3 that we know, but I want to be able to go ahead and calculate this for 90, 95, 99, 85, like if someone had a particular need for a different confidence interval. Okay, so we're going to look back at the notes for a second. Okay, so for a given confidence level, right, we want to be able to find the z sub alpha over 2. Now, in these problems, this is usually the more confusing piece that students struggle with, so I just wanted to break it down and bring it up front before we go further into using the formula, which we just reviewed. Okay, so if I want a confidence level for a given value, I'm going to go ahead and draw the picture of the 68.26 confidence level. It's a picture we should be pretty, we're getting pretty good at this picture. All right, so what we know is if we want 0.6826 in the middle, then in both tails, we have 1 minus 6826 divided by 2. 1 minus 0.6826 in the 2 tails. So in each tail, we have to divide that by 2. Okay, and in the notes, we have alpha as the numerator here, 1 minus the confidence level, right? And then alpha over 2. is this, the area in one tail. Okay, and in this case, if you take some moment, so the numerator is 0.31 for the arithmetic, it's always a little informative. So alpha is 0.3174, and alpha over 2 is 0.1587. So we have 0.1587 in each tail, and we want to know what is the z-score. What are these values? That delimit the curve in the following manner: 6826 in the middle and 0.1587 in each tail. So we can look up the left tail here, and if you go into the table and look that up, you will see. You might know without looking it up, right? That's minus 1.00 and 1.00. Those are the two z-scores that delimit the curve. This is the first part of the empirical rule. Okay, so that's how we use it for a familiar value. I'm going to go ahead and put 90% in the middle, and then we're going to calculate the delimiting values, that the z-scores that draw this picture for the 90% in the middle. Okay, so 90% comes into the middle here. So the area. Okay. Yeah, so we do 90% here. So the question is, we know that this is some negative value and this is some positive value. They're opposites of each other. And what is that? So alpha, the confidence level, let me just write this here, is 0.90, right? And from the confidence level being 0.90, alpha is 1 minus your confidence level, is 1 minus 0.90. So alpha is 0.10. Ooh, excuse me. 0.1. Okay, I'm just going to put this in a box here so it steps aside from all the other things that are on the board. It's very central and contained argument. So alpha is 0.01, alpha over 2, 0.1 over 2, 0.05. Okay. Now we're looking for z sub alpha over 2. We have our picture here. So we're looking for z sub 0.05. Going to get that formula card. Do the indirect lookup on 0.05. It's going to give you the left tail, right? So go ahead and look up indirect 0.05. Negative 1.64 or negative 1.65. It's right in the middle. So let's go ahead and call it negative 1. Let's call it 1. Actually, the z value here is the positive version of the number. And since we're right in the middle, usually we go to the closest, but since we're right in the middle, we'll just take it halfway. 1.645. Okay. And so the picture is minus z is equal to negative 1.645 and plus z is equal to 1.645, 90% in the middle, 5% in each tail. Okay. So that gives us, that's sort of how we're going to go ahead and calculate that z sub alpha over 2. And let's go ahead and look at the notes again. So as we kind of scroll through the notes, you see we have our recipe, which I usually do like to just take a moment, not too long, right? So we're looking for, we want to find the confidence interval and the assumptions or conditions that we've used in the process to come up with the procedure for the confidence interval is that we are using normality of X bar. So this is valid if the population is normal or if there's a large sample size, n is greater than or equal to 30. Okay, and that means that X bar would be normally distributed or approximately normally distributed. And additionally, we are assuming that sigma is available, so we know that we know sigma is known. So the first step is to calculate the sigma sub x, the z sub alpha over 2. And then the second step is to put it in this formula. And then the third step is to interpret the confidence intervals. So those two red statements in the notes that we had just looked through. Okay, so it's really important to only use this procedure when, in fact, you either have normality of the parent population or a large sample size. So if you need to graph the data to confirm that you have, if you have a small sample size, you might need to go ahead and graph the data before you jump in and use this process. Okay, so I want to go through this example. I'll go ahead and take it over onto the board. Hi, so I want to look at that example in the notes. Consider the ages of 50 random selected people with a population standard deviation of 12.1 years and a sample mean of 36.4 years. Find the 95% confidence interval for the population mean of their ages. Okay, so I already pulled out the important information from the problem. We have a sample size of 50. We know that the population standard deviation is 12.1 years, and the sample mean of their ages is 36.4 years. And we're asked for the 95% confidence level. So the first thing we want to do is we want to go over here, and I write it in this little box because I want to set it aside from all of the other information and values in the problem, that the only thing that helps us to get the z sub alpha over 2, which we need, right, that's the first step in this problem, is all we need is the confidence level. So anything else about the data or the distribution isn't really informing this sweep through. So the confidence level is 0.95. 1 minus the confidence level is 1 minus 0.95, 0.05. All right, so just pushing it through our little box. Alpha over 2 is 0.05 over 2, 0.025, right? And z sub alpha over 2. We're looking for z sub 0.025. So go into the table, please, and do an indirect lookup here on 0.025. And we hit right on the nose with this one, 1.96. Remember, this is the positive version. So 1.96. That's my z sub alpha over 2. So we say the confidence level of 0.95 gives us a z sub 0.025 of 1.96. All right, so let's go ahead and use your formula for confidence interval, x bar minus z sub alpha over 2 times sigma over the square root of n. That's the lower bound. And the upper bound, x bar plus z sub alpha over 2 times sigma over the square root of n. So substituting in, x bar is 36.4, z sub alpha over 2 is 1.96, sigma is 12.1, and the sample size was 50. $36.4 plus 1.96 times 12.1 over the square root of 50. Okay, so how I work these problems out and how I found my students have most success is we're always going to get this thing that's dangling here. So this piece right here, 1.96 times 2.1 over the square root of 50, mouthful. That's called the margin of error. And we're going to calculate it first. It's the same, so then we'll add it and subtract it from the population mean. So just take a second and work through the calculation. Okay, and so coming back into the notes to wrap the problem up, we have here that margin of error is 3.35. So our confidence interval goes from 36.4 minus 3.35 to 36.4 plus 3.35. And which gives us a lower bound of 33.0 and an upper bound of 39.8. And here are the interpretations. So anytime you are required to give a confidence interval, you are required to also interpret the interval. So you give an interval of numbers, a confidence level, and an interpretation. So all three of those things are required every time, even if they're not asked for, okay? Because the confidence interval itself really are those three pieces. So we are 95% confident that the population mean falls in the interval 33.0 to 39.8. And that's the shorter interpretation, and the longer interpretation is, if we repeat this experiment a large number of times, many samples of size 50, and each time we construct the 99% confidence interval, we would expect that 95% of the time, the confidence interval contains the population mean. All right, so that's the longer one. All right, so that's it. That's it for section 8.2. We'll have some practice in class. You'll have some practice also in the two kinds of homework. So I'll see you in class. Bye.